Hello and welcome to the Cyber1 YouTube channel. My name is Ray, and in this video, part 9 of SpotMicro, we're going to download and install the program that I've developed for the SpotMicro to run on MyRobotLab that we installed last video. Alright, so we're going to need a terminal window, because we're always going to need a terminal window when we're setting up MyRobotLab or doing any really interesting stuff in Linux, any type. I'm also going to use a web browser. So in this case, I'm looking for a particular link. So github.com. Now this page does take a little bit of time to load. So I'm going to search for SpotMicro MRL, and you'll find that there is the one repository. This is the one I've created. Cool. So what we're looking for is this link. So if we click on there, you should copy it into the clipboard. So now we can go git clone, and if I right click the mouse and paste, we get the full address from the clipboard and it will download. Now it won't take long to do this. There's not a lot in there. Most of the heavy work is done by MyRobotLab, and we're just running scripts to tell it what services to start. I will have to rewrite this at some stage down the track when they're finished improving the setup of MyRobotLab. Now, if you remember from the last video, we are running the Nixie version, which is a development version. I've now got version 701 installed on this Raspberry Pi. Since the last video, I also did a little bit of an upgrade. I replaced the Raspberry Pi 3 that was installed in the videos with a Raspberry Pi 4. Now I've also made a couple of other little changes, including changing all the servos for Caro F39202-270 degree digital servos. These are a 7.2 volt servo, so I can run them off the S2 battery pack without needing a voltage regulator or switch mode power supply. I haven't removed the old switch mode power supply, although the servos are not connected to it. But one of the other changes I made is I relocated where I mounted the Arduino and moved it forward in the body in between the front shoulders. That freed up space for a second PCA 9685, which I'm now powering from that second switch mode power supply. I've named it front in the program. The original one is named back, as it was. Actually, I don't think I named it last time. But let's have a look at this program anyway. So I don't need a web browser anymore at this stage, but I do need a Windows, my folder view file manager. Okay, so we've now got this SpotMicro MyRobotLab. This wasn't in the system previously. The Spot clone creates this whole folder, and it literally copies everything from GitHub down onto this Raspberry Pi. And it's not an overly large folder, 2.6 meg, so it's not really huge. We will need to take this Spot folder and this Spot SH. So SH stands for shell, So this is a shell file, but there's a little catch with it, and I'll get to that in a minute. We're going to put it into MRL 1.1.701, which is the latest version I've got installed. Copy and paste. I have had this in here before, so I'll just do a full overwrite. Now, one of the advantages of doing this is I can now CD SpotMicro MRL. Incidentally, the way I completed that line quickly is just use tab ls, and that's the directories and files that are in that SpotMicro MRL. But if we go git pull, it'll actually check with GitHub and make sure it's all up to date. So as long as we don't change any of the files in here, it's quite happy to just pull down the new ones and overwrite the old ones. So any changes I make, if I make a major change to the program, I'll let people know, and you can actually download the latest. If you go into the CyberOne Discord, there is also within the Discord a channel in there called GitHub, and in GitHub you can see whenever I make changes to any of the, or either of the Fred or the SpotMicro GitHub pages. GitHub updates it's called. So whenever I make a change, you can see it's been made and which one I made changes to. Alright, so let's just go back one level. Select the terminal. CD. And then CD MRL 1.1.701. Alright, so we've got a number of files there. Now you might note there's color coding going on here as well. So MyRobotLab.sh is green, which means it can be executed, but Spot.sh is not. So it will not execute. There is no permission for it to execute. So let's come back over to here. Right click on Spot.sh, Properties. Go to Permissions, and you'll see the execute is set to nobody. So we're going to have to change that. Now you can set it for just yourself, or you can set it to anybody. I just generally set it to anybody. Now if we come back to the terminal and repeat that command, you'll now see that Spot.sh is now green. So we can now go dot, meaning current directory, /spot.sh. Now remember, Linux is case sensitive, so a lowercase spot starting with lowercase is different to a spot starting with uppercase, unlike Windows, which is case insensitive on file names. In this case I created it with an upper, and so we need to use a capital S in Spot. And this will start MyRobotLab. Now, unlike the MyRobotLab.sh, this will not launch the web browser. There's pros and cons to that. One of the cons is we can't see what's going on, but one of the pros is we can actually open it up on a different computer. Okay, so before we look at the web page that's associated with the SpotMicro or the MyRobotLab operating system, I just want to go over the program that we just started. Okay, so the shell script file is basically a copy of the MyRobotLab.shell file with a variation on what I'm launching with MyRobotLab. So in the shell script for MyRobotLab, it's going to, and this is the line down the bottom, it's going to invoke the Python execute file and run start.py. In the MyRobotLab one, it also launches the web GUI and the web browser so that you have an interface. Because SpotMicro doesn't have anything connected to its video output on the card at all, it's very difficult to use that. It's also a lot easier on the processor if it's not running Chrome on that same little computer. Remember, the Raspberry Pi 4 is a relatively small computer. So all it's doing, it's a copy of the MyRobotLab one, and I've just modified this line 64 so that it's only launching the start.py. So let's have a look at start.py. Start.py, I've put a lot of comments in this file, so before you run it you can have a good read through to see how it works, and I've tried to put as much explanation in there as I can without going over the top. In the configuration file, so system config, there is an option to actually run the web GUI on the local machine, so on the Raspberry Pi in Spot. My config has got it set turned off, but let's just step back a bit. Running folder is Spot, execute file, configuration, system config. So this is this system config here, and in here the robot web named is Spot, run web GUI is true, but run the web GUI browser is false. So we want to start the web GUI. GUI stands for Graphical User Interface, but we don't want to start the web browser. So let's go back to start. So web GUI is true, so we're starting the web GUI, but we're not starting the web browser. The next thing we're going to do is execute a file called common variables. Common variables are different variables that are used throughout the program on a global level. So in here I've got things like the foot positions for the X, Y and Z axis for each of the 4 feet. I've used the naming convention FL for the front left, FR for the front right, BL for the back left, BR for the back right. And then I've got the X, Y and Z axis. I've also put in here the distances that I've measured between joint axes on different parts of the leg. If you use modified legs or parts or a longer body, you will need to go through and review all of this and update the values as suited to your own robot. I've got in the last left ping and last right ping so that we can coordinate the 2 ultrasonic sensors. There's no point trying to run them both at exactly the same time, so we fire one, get a result, then fire the other and get another result. If you fire them both at the same time, you can get conflicting results with false echoes. And the emotional state is something that's still in works. That may yet change. Okay, so let's go back to start. Alright, so the next thing we execute is controllers pi. So this is where we load in all of the controllers that we're going to be using. So controllers pi, first thing it does is it loads in the config. So controllers.config. So enable nano. Arduino Nano is false. True for on, false for off. That would explain an error I got during startup. So with this, I'm specifying dev TTY AMA0 because that is where I've connected my Arduino. We've also enabled the Raspberry Pi because we're running it on a Raspberry Pi. And down here we've got the 16 channel servo drivers, and there's 2 of those. I haven't added provision for any more other controllers in here, because quite frankly I don't know where you'd physically fit any more controllers. Let's have a look at the actual controllers themselves, and in here the first thing we do is we check and see if we're running it on a Raspberry Pi, which we are, and so we start the Raspberry Pi service. Now it's very important that we do have the Raspberry Pi service, because in this case we're using the I2C bus that's on the Raspberry Pi, and you can't use that if it doesn't exist. Right, enable Arduino Nano. So if it's true, it will start the Arduino Nano. It'll set the board type to Nano, because that's all we've really got room in there for, and then we will configure the Arduino Nano COM port, and this is actually specified in the config. I've also created 2 other files to help with testing to make sure you're using a little bit of sense when setting your configurations. So if you disabled the the Raspberry Pi, and then you tried to start one of the PCA 9685 servo drivers using the Raspberry Pi in the config, that's not going to work, and it's just going to throw errors. So I've created this little file. It's called test I2C controller exists, and it just checks to see if the controller that you've specified has actually been started. If it has, it returns yeah, all good. If it doesn't, it'll actually turn it off or disable that function, and I'll show you that one working a little bit later. I've also done the same thing for the Arduino. So this should disable the ultrasonics if the Arduino isn't enabled. Alright, so with this the PCA 9685 controllers, here's where I'm actually using that test I2C controller exists function, and we actually will flip this enable to false if the Raspberry Pi is not set. It is also possible to use the Arduino as a I2C bus controller, so you can set these things to use the Arduino, in which case it'll check the Arduino instead of the Raspberry Pi. So we have the back, which is our primary unit, and then we have the front, which is the front one. Now the reason why I've added the front one in is on the 3D prints I did for the head, the Raspberry Pi camera holder has provision for 4 LEDs. Now the LEDs I have are a 5mm RGB LED. That is, they have 4 pins on them, a common anode I think it is, and 3 cathodes, one for red, one for green, one for blue, and so I can connect each one of those to a different pin on the PCA 9685. Now a little known fact on that particular chip, while Adafruit have discovered that it works really well for servo control, it was originally designed as an LED dimmer control. So we will be using that feature to drive these LEDs. Now having 4 LEDs with 3 pins each that I have to control, that's a total of 12 of the outputs. So there weren't enough left with the 4 that we had on the back servo driver, so we'll use a second one to drive the LEDs. Now the LED, I may have mentioned that I added a second PCA in there, and with larger servos in there that run on high voltage. They're connected directly to the batteries now, so that gave me a spare 5V switch mode power supply that I can use to drive the LEDs. It also means that if I wanted to, down the track, I can mount on the top some small servo based arms so that we can put an arm on it like the Spot from Boston Dynamics has as an option. At this point I also created this file test servo controller exists, and I've listed both the front, the back and the Arduino Nano as servo controllers. So when we're adding servos later, we can actually check to make sure that our servos exist. Alright, so let's go back to our start Pi. So we've started our controllers. Next one is our I/O. So I/O's at the top here. You'll be starting to get familiar with this configuration layout, where the first thing we do is we load the configuration file. So we've got the configuration file here, where we enable the ultrasonics. We specify whether it's connected to and what pins we're connecting it to. And we do that for both the ultrasonics. I've also got provision for a battery monitor with the Arduino. The way I've modified it, I've put in provision for one at this stage. Well, there's provision here for 2 battery monitorings. I've actually got one connected stage. From a physical hardware perspective, I'll come back to more on that a little bit later, probably in another video. And we can specify which inputs. So I've connected to A0. I need to go over that as a separate video anyway, because I'm using voltage dividers and I want to go through how that works. Alright, the MPU 6050 is an inertial measurement unit. That is, it can feel acceleration on the body of that device, both in rotational and linear axes. This allows our robot to know, if it's standing straight and steady, or if it's falling over, or if it's moving. And that's going to become handy later as we develop the program, so that it can actually walk and balance. Now on the back is a HD 44780 2-line 16 character I2C LCD display. Now some people are opting to not use it, so you have the option to disable it here by setting the enable LCD to false. I've got it installed. You can also change your start message in here. So my startup message is Cyber1 Spot and MyRobotLab Micro. So when it appears on the robot, it'll come up as SpotMicro. It'll literally look exactly like that. Mine is on address 027. Different makes and manufacturers have actually had these designed to work on different addresses, and on the LCD display there is actually jumpers that you can change its address. So you may need to go to the Raspberry Pi service and actually scan the I2C bus to find out which one you've got. So just start it up with MyRobotLab.sh in this case and scan the bus, and that'll give you all the addresses that are used. You'll have to start the Raspberry Pi service first before you can do that, of course. Let's go back to the I/O, and here we are actually starting up the left and right ultrasonic sensors. So this is a program that's still in development, so while I'm starting the services, I haven't yet used them. That will come in later videos as I actually develop the program further. So it's pretty straightforward. We do a check to see if there is a pin enabling device. So in this case, we're checking to test to make sure the Arduino controller exists, and if it does, we then will start the service. One of the first things I do when I have confirmed that the service is running is with the Arduino Nano pin mode 2, I'm setting it to an output. Now if you remember from the video where I did the wiring, I actually used pin 2 to power the 2 ultrasonic rangefinders. So we need to turn it to an output, and then we need to turn it on. So that's these two lines, and I've done it on both of them. We start up the ultrasonic service. We set the trigger pin to be pin 1 and the echo pin to be the other one. So it actually triggers the ultrasonic using one of the pins and receives a pulse back, so it listens on the other one. And then we go through and do the attachment to make sure it attaches it correctly. Now, runtime get service is a really cool little feature. Sometimes you need to actually pass through a link to the service itself, but you don't necessarily have access to it. So you can, in actual fact, ask runtime for a copy of that link, and it will give it to you. So I've given it the name of the ultrasonic, and it works. In this case, the right ultrasonic attachment point is the Arduino from the configuration file, Arduino Nano. Now, in the comment here, I have actually shown how you can actually run your own little bit of code to get a callback to your own routines, and I'll show how they work a little bit later on. That way, when you do a range on it, it'll actually call your routine when you've finished ranging. This is the routine for running the battery monitor, and this is where it goes through and configures pins as analog inputs, and then puts a capture on it, able to call back into your own. In this case, we're using a program called Battery Mon Publish Pins. So Jeff is defining a method of program, and down here we will actually set up our add listener for the Arduino, and it will capture that. So for those who don't know about MyRobotLab and how it works, it uses a lot of publication and subscription. So you can subscribe to a publication. So in this case, I'm subscribing to the pin publishing of the Arduino, so I can actually see when pin events occur, and then we can actually filter that and use that information. And this will be used to capture our battery value. Okay, MPU 6050. Now, you can have up to 2 of these on the one I2C bus, so I've put in provision for 2 of them. I'm only using one, but there is provision for a second one. Not quite sure why you would put a second one in, unless we modify the head to something that can swing the head around, and you might put one in the head as well. But the code's there. There is a possibility you could do it. And then I've got the service start for the 2-line 16-character LCD display on the back. Now the thing with the L2 or the I2C LCD display is the LCD display is actually a parallel device. It's not an I2C device inherently, but a lot of them will now ship listed as I2C by adding what's known as the PCF8574 chip on it to actually drive the pins. This is a 8-channel I/O expander, and it is also supported by MyRobotLab. So when we're using this LCD display, the first thing we need to do is create the PCF8574 service, which we do. Connect it to the bus. In this case, it'll be bus 1. Set the address on it, and then attach it to the appropriate I2C bus controller. In my default config, it is the Raspberry Pi's bus controller. Just a note, if you connect this to the Arduino bus controller, you will want to set the LCD bus to 0. Once we've got the PCF8574 running, then we can start the LCD display itself, which is the HD44780 chip. Now this chipset can be used for a single line, a 2-line, or a 4-line LCD display. The The code is exactly the same. There's no configuration in the code as such to make it work. We attach it to our PCA 9685. We clear the display, and then we send out the two messages on line 0 and line 1. Like a lot of things in computing, this is indexed from 0. I then make sure the backlight is turned on, so set to true. If you like these videos, don't forget to click on like, subscribe, ring that notification bell so you know when the next video is released. I have a Discord channel. The link will be in the description to the Discord channel. There'll also be a link in the description to the GitHub files as well, the repository, so it's easier to find. I also have a Patreon account where you can join my VIPs Go Lucky and Lorenz Berger, and my other Patreons Elmerels 45 and Ratchet. And we will see you in the next video.